Welcome to this explainer. Today, we're diving right into the fascinating physics and chemistry behind why things glow. We're going to break down the exact mechanics of what we call cold light. You know, everything from those instantaneous, brilliant flashes to that eerie, delayed, ghostly luminescence. And crucially, we'll see how these molecular quirks are actually driving some of today's most cutting-edge detection technologies.
Here is our roadmap for today. We'll start with the family tree of light, take a quantum journey, look at the structural rulebook, explore the vulnerability of phosphorescence, dive into light from chemistry, and finally wrap up with measuring the invisible. Let's get to it. Section 1. The family tree of light, categorizing cold light.
Okay, so luminescence is essentially cold light. Think about a traditional incandescent light bulb. It glows because it gets extremely hot, right? Well, luminescent materials completely bypass that. They emit light without all that extreme heat. Now, if you look at the family tree here, it basically splits into two main branches based on what actually triggers the glow. On one side, we have photoluminescence. This is light triggered by absorbing external light, and it splits further into fast fluorescence and slow phosphorescence. On the completely other side, chemiluminescence, where the glow is triggered purely by a chemical reaction.
Moving on to Section 2. The quantum journey. What happens inside the atom?
To really grasp the difference between these branches, we need to zoom way in and track a single photon through three distinct steps. Step 1 is absorption. Basically, an electron absorbs some external energy and just instantly jumps up to a highly energetic, excited state. Then comes step 2, relaxation. The molecule starts vibrating and immediately loses a little chunk of that newly acquired energy as physical heat. Finally, step 3 is where things get interesting, the split path. That excited electron has to return to its ground state, and it basically has to decide, do I drop down immediately and create a flash of fluorescence, or do I take a weird, delayed route to create phosphorescence?
So what exactly causes that delayed route? Well, it's all about a microscopic spin flip inside what's called the excited triplet state. Imagine the excited electron literally flipping its quantum spin to match the electron it left behind. The catch? Quantum rules strictly dictate that these electrons cannot recombine while they're spinning the exact same way. It creates what physicists call a quantum forbidden transition. It's basically a microscopic traffic jam, and that tiny quantum traffic jam is exactly what causes the massive, sometimes hours-long delay we see in phosphorescence.
Now, remember that second step we just talked about where some energy is lost as vibrational heat? Because of that, the light that finally gets emitted always has lower energy than the light that initially went in. And in physics, lower energy means a longer wavelength. This visible gap between the absorbed light and the emitted light is known as the Stokes shift. You can think of it like a cosmic tax. A little bit of energy just naturally jiggles away into the environment as heat before the actual glow can even happen.
Section 3. The structural rulebook. Which molecules glow?
When we're evaluating any glowing material, the absolute most crucial metric is its quantum yield, which we represent with the Greek letter phi. It's actually a super simple ratio. It just measures exactly how efficiently a molecule turns absorbed energy into visible light. So, if a molecule absorbs 100 photons and emits 100 photons, boom, its quantum yield is a perfect 1. But if it absorbs 100 photons and just heats up without emitting a single drop of light, its yield is a flat 0.
So what exactly makes a molecule score that perfect 1? One word, rigidity. A highly efficient molecule like fluorine acts like a locked vault. It has these tightly fused aromatic rings locked together by chemical bonds. Because it physically cannot bend or vibrate, it's literally forced to release its extra energy as light. But then look at a flexible molecule, like biphenyl. It acts more like a wobbly spring. It takes that same excitation energy and just jiggles it away through physical motion. The energy is wasted as useless heat instead of beautiful light. Basically, structure absolutely dictates the light.
Section 4. The vulnerability of phosphorescence. Protecting the glow.
Remember that beautifully delayed glow of phosphorescence we talked about earlier? Well, it turns out it comes with a massive practical hurdle, the vulnerability of time. Because phosphorescence takes anywhere from a fraction of a millisecond to literally hours, those excited molecules are just sitting there, totally vulnerable, waiting to emit their photon. And during that long wait, they almost always crash into oxygen or other molecules in their environment, losing their precious energy to physical collisions before they even get a chance to glow. To stop this, scientists often have to freeze the samples solid, sometimes using liquid nitrogen, just to completely halt those collisions and protect that delayed photon.
In fact, environmental factors like high heat or thin, watery solvents are absolute killers to this delicate process. Think about it.
High temperatures mean the molecules are energized, moving faster and crashing into each other way more often. And low solvent viscosity? That just means the molecules can swim around freely, which, you guessed it, leads to even more crashes. Every single crash acts like a tiny energy leak, rapidly draining that excited state energy and absolutely tanking your overall quantum yield.
Section 5. Light from chemistry, illumination without lamps. All right, let's shift gears completely. This is where chemiluminescence really shines. Here, we're not using external light at all. The excited state is achieved purely through a potent chemical reaction, often by mixing the sample with strong oxidants like ozone or peroxide. And here's why this is a massive deal for detection technologies. Because there is absolutely zero background light from an external lamp to interfere with our sensors, the detection sensitivity here is totally unparalleled. We're talking about achieving limits down to parts per billion. And you know what's amazing? Nature completely beat us to this. Bioluminescence, that incredible glow you see in fireflies, deep-sea jellyfish, or glowing marine bacteria, it isn't magic. It is simply this exact same chemoluminescent reaction happening naturally inside a living creature. They're just mixing chemicals to excite electrons and create light in the dark. It's brilliant. Section 6. Measuring the invisible. How do we capture this?
So this brings up a massive practical challenge for the types of luminescence that actually do require an external light source. How on earth do you measure an incredibly faint fluorescent glow without completely blinding your highly sensitive equipment? It's the ultimate optical paradox. You literally have to blast a sample with a super intense beam of light to force it to glow, but that intense excitation beam will instantly wash out the remarkably faint glow you're trying to measure. It's kind of like trying to see a single match being struck while you're staring directly into a car's high beams.
The engineering solution inside standard spectrofluorometers is actually remarkably simple, but it's a total breakthrough: the 90-degree rule. Instead of sitting right behind the sample, detectors are positioned at a perfect right angle. The intense excitation beam shoots straight through, while the 90-degree detector safely catches only the multidirectional, scattered glow radiating off the sample itself. Pretty clever, right?
Scientists use this ingenious 90-degree setup in two distinct ways as practical analytical tools. First, there are direct methods, where adding more of your target chemical literally creates more of a glowing complex. So a brighter light simply means a higher concentration. But then there are indirect or quenching methods. Here, the target chemical actually acts like a microscopic dimmer switch. You start with a brightly glowing sample, and as you introduce the unknown chemical, it physically suppresses the light. So in this case, less light actually means a higher concentration of your target.
To synthesize everything we've covered, this table is basically our master cheat sheet. It directly compares our three main glow architectures. Notice how fluorescence and phosphorescence share the electromagnetic light trigger, but utilize entirely different quantum spin states. That's what leads to that massive difference in emission lifetime, from instant flashes to deeply delayed glows. Meanwhile, chemiluminescence stands alone, trading external light triggers entirely for raw chemical reactions.
Ultimately, the entire field of luminescence spectroscopy rests on these core pillars. First, it's a story of energy transformation, always dropping from high energy to low energy. Second, it relies on the absolute rule that molecular structure dictates light. Rigid vaults glow while wobbly springs stay dark. And finally, by leveraging the blackness of a 90-degree angle, we achieve extreme analytical sensitivity, allowing us to see the microscopic world like never before.
As chemists and physicists continue to engineer molecular structures, learning to lock atomic energy into tighter and tighter vaults, we have to ask ourselves, what invisible, microscopic worlds will these custom-built, unbreakable glowing molecules illuminate for our industry next? The future of materials science is incredibly bright. Thanks so much for joining me for this explainer, and keep questioning what you see.